Greetings students. In this video, we are going to discuss how to identify the queuing model MM1 KFIFO and how to solve it. So the model we are going to discuss today is single server finite capacity model. Okay, single server finite capacity model. So let us see how to identify this model by taking one problem. So consider this problem. Consider the problem that patient arrive at a clinic according to a Poisson distribution at a rate of 30 patients per hour. So patients arrive at a clinic means there is a single server. Okay. A clinic denotes server is 1. According to a Poisson distribution at the rate of 30 patients per hour. Next, we have to see anything is given about the capacity. Okay. So the waiting room cannot accommodate more than 14 patients. So here waiting room is the capacity. They are telling it cannot accommodate more than 14 patients. Means the capacity of the waiting room is 14 patients. So finite capacity. So this comes under single server finite capacity model. So we have identified this problem as a model MM1 KFIFO single server finite capacity model. Okay. Next step is to identify the arrival rate and service rate. Arrival rate is denoted as lambda and service rate is denoted as mu. Okay. So lambda denotes the arrival rate. Okay. So check what is given in the question. Patients arrive to the clinic at a rate of 30 patients per hour. So the question itself, arrival rate is directly given. So we'll take it as mu. In the previous video, we have seen that instead of arrival rate, they have given the mean arrival, average arrival. In that case, we'll take the reciprocal. Here directly they have given the arrival rate. So as such, we'll be taking. So arrival rate is given as 30 patients per hour. So lambda is 30 per hour. Okay. And then examination time per patient. Examination time denotes what? Service rate. Service rate per patient is exponential at the rate of 20 per hour. So rate, here also rate is directly given. So we'll write as such. So mu is equal to 20 per hour. Okay. So lambda and mu are directly given. Next step. What is the notation for the question asked? First question, find the effective arrival rate at the clinic. Effective arrival rate is being asked. What is effective arrival rate? The notation is mu. Okay. So this terminology, effective arrival, you will use only for the finite capacity model. Whenever the capacity of the system is finite, in that model, we'll use effective arrival, that is lambda dash. That formula varies from model to model. Only for finite capacity model. So this is single server finite capacity. So we will have lambda dash effective arrival. As well as for multi-server finite capacity also, you will have effective arrival. So only in these two models where the capacity is finite, we will have effective arrival lambda dash. What is the formula? We'll see later. But first subdivision is you have to find lambda dash. Next subdivision, what is the probability that an arriving patient will not wait? So they are asking you the probability that arriving patient will not wait. Means what? The patient need not wait. He'll directly get into the service. When it will be possible? Only when the system is idle. That is, nobody is there in the system. That is, P naught is asked. What is the probability that the arriving customer will directly go to the service? Okay. So you have to find P naught. Third subdivision, what is the expected waiting time until a patient is discharged from the clinic? So what is the expected waiting time? So waiting time is asked, so W. Whether it is WS or WQ, that you have to take from the question. What is the expected waiting time until a patient is discharged from the clinic. From the clinic. Clinic denotes the system. So what is the time he spends in the system? So WS. Okay. So these are all the things being asked. So we'll find it one by one. Before that, let us see what is the formula we'll use for this model. So this is the formula we have to be thorough with for this model. Single server finite capacity. As usual, Little's formula. Little's formulas, LS is equal to lambda WS, LQ is equal to lambda WQ, WQ is equal to WS minus 1 by mu, LS is equal to LQ plus lambda dash by mu. So here in the general Little's formula, instead of lambda, you will be using effective arrival lambda dash. That is the only difference for finite capacity model. Okay. So here what is lambda dash denotes? Effective arrival, that is given as mu into 1 minus P naught. The formula is mu into 1 minus P naught. And these are all the set of formula we should remember. P naught. P naught denotes what? Probability that the system is empty. That is nobody is there in the system. That is P naught. It is given as the formula 1 minus rho divided by 1 minus rho per K plus 1 if lambda is not equal to mu. That is arrival rate is not equal to service rate. Then we'll use this formula. If suppose arrival is equal to service, we'll use 1 by K plus 1. Here as usual, rho denotes lambda by mu, that ratio. Okay, so Pn denotes probability that there are n customers in the system. It is given by the formula rho per n P naught. Okay, rho denotes lambda by mu, P naught denotes, P naught you can calculate by using this previous formula. Next, probability that a customer turned away. When will the customer turned away? When the capacity is full, the coming customer cannot wait, so he will turn away. So probability that the customer turn away is nothing but probability that already there are K customers in the system. Same formula, Pn in the place of n, we'll use K, rho per K, P naught. Okay, so if they ask you what is the probability that a customer turned away means, we have to find Pk. Okay, next, as I said in the previous video, in every model, in the 4 identities, that is LS, LQ, WS, WQ, we have to memorize only one. Remaining, we can calculate using Little's formula. So in this single server finite capacity model, we have to memorize LS. Okay, LS denotes what? Yes, length of the system. Okay, so length of the system we have to memorize in this model. It is given by the formula rho by 1 minus rho minus K plus 1 rho per K plus 1 by 1 minus rho per K plus 1. This is for lambda not equal to mu. If lambda is equal to mu, it is simply K by 2. Okay, so LS we have to memorize. If we have been asked to find LQ, WS, WQ, everything we can get from LS. Okay, so if we know LS, we can find WS as LS by lambda dash. Once we know WS, we can find WQ as WS minus 1 by mu. Once we know WQ, we can find LQ as WQ into lambda dash. We can use Little's formula to find the remaining identities. So in this model single server finite capacity, we have to memorize these 4 formula along with the effective rate lambda dash formula. Okay, coming back to the question. So now we have identified the question as single server finite capacity. What exactly is the K? Value of K we have to take from the question. What is K here? The waiting room cannot accommodate more than 14 patients. So the capacity of waiting room is 14 patients. So what is the capacity of the system? So K denotes capacity of the system. What is capacity of the system? Capacity of the waiting room. Capacity of the waiting room plus 1 will be in the service. One patient will be under examination, no? So that the 1 patient in the service also we have to include. That is the patient in the service. That is 1. Capacity of the system in this formula, in this problem is 14 plus 1 patient in the service. That is 1 patient in the examination. All together gives the capacity of the system. Okay. So in the question, they have given only capacity of the waiting room. So K denotes capacity of the system. So we should be very careful in finding K. So remember, K denotes capacity of the system. Okay, so here in this problem, K is 15. So we have got lambda, we have got mu, and we have found out K. So let us proceed to find the remaining values. So we'll find, as you know, lambda and mu. Go ahead to find rho. Rho is lambda by mu, which is 30 by 20, that is 3 by 2, that is 1.5. So in this problem, rho is 1.5. Next, what is the first subdivision? It's been asked, find the effective arrival rate at the clinic. That is, we have to find lambda dash first. So what is the formula to find effective arrival rate? That is lambda dash. Lambda dash is given by mu into 1 minus P naught. So to substitute this, we need P naught. What is P naught? P naught is given by the formula 1 minus rho divided by 1 minus rho per K plus 1. So which is equal to 1 minus rho is 1.5 and 1 minus 1.5 the whole part K plus 1, that is 15. Okay, simplifying this, we'll get P naught as 0.00076. Then what is lambda dash? Mu into mu is 20, 1 minus P naught. Okay, so simplifying this, lambda naught is 20, unit is hour. So lambda dash is 20 per hour. Second subdivision is, we have to find what is the probability that an arriving patient will not wait. That is, the system is idle, empty. There are no customers in the system. So probability that arriving customer need not wait is nothing but P naught. Already we have found it out as 0.00076. Already we have found P naught. Okay. So directly we write the value. Third subdivision, what is the expected waiting time until a patient is discharged from the clinic? So waiting time in the system. That is, using Little's formula, WS is given as, we can use WS formula in terms of LS, because only LS formula we know. So WS is equal to LS divided by lambda dash. What is the formula to find LS here? LS can be calculated using the formula rho by 1 minus rho minus K plus 1 rho per K plus 1 by 1 minus rho per K plus 1. So LS is equal to, where, let us find LS first. LS is equal to rho by 1 minus rho minus K plus 1 rho per K plus 1 divided by 1 minus rho per K plus 1. What is rho? 1.5. So 1.5 divided by 1 minus 1.5 minus K plus 1 is 15. 1.5 the whole power 15 divided by 1 minus 1.5 the whole power 15. Simplifying this, we'll get LS as 13.02. So WS, that is waiting time in the system. That is the patient expected waiting time until a patient is discharged from the clinic. That is the expected waiting time in the system. System is clinic here. So WS is LS by lambda dash. That is 13.02 divided by lambda dash is 20. That is 39. The answer. Okay. Okay. So remember, in this model, that is single server finite capacity model, wherever we have the capacity as finite, in Little's formula, instead of lambda, that is arrival rate, we will be using effective arrival rate lambda dash. Here in this model, lambda dash formula is mu into 1 minus P naught. Remember, only in Little's formula, we will be using this arrival, effective arrival. Remaining formula like P naught, Pn, Pk and all, and Ls also, we will be using only lambda as the arrival. So rho is lambda by mu only here. Only in Little's formula, we will be using effective arrival instead of lambda. Hope you are all clear with the single server finite capacity model.